All right, so here we go. It says in downhill speed skiing, a skier is retarded by both drag and kinetic friction on the skis. So in A, it says suppose the slope angle is 40 degrees and the snow is dry with a coefficient of kinetic friction of 0.04, mass of the skier, blah, 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 blah. So we've got all this information. All right, so let's start by writing all that information down. So here's what we know. We know that our angle is going to be 40 degrees. We know that our coefficient of kinetic friction is going to end up being 85. No, it isn't. Sorry. Our coefficient of kinetic friction is very low, 0.0400. The mass of the skier is 85 kilograms, sloppy sig digs. Cross-sectional area of the skier, he's tucked into a little crouched position, so it's 1.30 square meters. Drag coefficient is 0.150, and the density of the air is 1.20 kilograms per cubic meter. All right? And it wants to know what's the terminal speed. So remember, terminal speed is accomplished when your net force is 0, okay? So here's what I'm looking at. So we've got the skier, right? So you gotta have a good drawing or it doesn't work. All right, so there's our skier. Oh, I guess we shouldn't put those because those will get in the way. All right, so what forces are there? Well, there's FG parallel. We can certainly calculate that, right? It's just going to be mg sine of 40 degrees, right? So if you calculate that, you end up getting, I'm going to make it negative 535.44 newtons. Okay? Now, there's going to be kinetic friction, right? So your force of kinetic friction you can find. Well, here, let me do this. So your FG parallel, if you find it, or sorry, perpendicular, if you find it, turns out to be 638, we'll make it negative 0.115 newtons. That means you're going to have a normal force of the same value, 638.115 newtons. So there's going to be a kinetic friction going up the hill, which is equal to this normal force times my coefficient of friction. So the force of kinetic friction ends up being 25.52 newtons, right? So when are we going to hit terminal velocity? Well, you're going to hit terminal velocity when your net force is 0, right? That's when we're going to stop accelerating. Remember, as he speeds up, this drag force is going to get bigger and bigger and bigger and bigger and bigger, but eventually it's going to make it so that our net force is 0. So our net force is 0 means that my force of gravity plus my force of kinetic friction plus my drag force have to cancel out. So you get 0 equals negative 535.44 plus 25.52 plus drag force, and solve it. And that drag force ends up being, it's really close to 510 newtons. So now you can use your drag force equation and solve for the velocity, right? So remember, drag force is 1/2 c rho a v squared. We know our drag force, so solve. So you get v equals, what is it, 2 times the drag force over c rho a, all square rootified, and plug in your numbers from over there, and you end up getting 66 meters a second. Okay? So that is that. Now for part B. Part B says if a skier can vary that drag force coefficient by a slight amount, dc, by adjusting, say, the hand positions, so he's moving his hands to change that coefficient, what's the corresponding variation in the terminal speed? So all we're going to do here is we want to come up with an expression for dv in terms of dc, right? So here's my equation for velocity. My velocity equation is, I'm going to rewrite it as an exponent. So it's 2fd over c rho a to the 1/2 power, right? And I want to come up with an expression for my change in velocity with respect to a change in that coefficient, right? So you just take the derivative and you get this 1/2 2fd over c rho a to the negative 1/2, and then you got to do chain rule, right? So now the derivative of this inside guy, ooh, yuck. No, this is wrong. Let me rewind. I'm sorry. I jumped ahead of myself. I wasn't thinking. Okay, so I am going to do this, but I'm going to rewrite it like this. This is the same as 2fd over rho a to the 1/2 times c to the negative 1/2, right? Cool. So now I can take my derivative. So I want to take the derivative of the velocity with respect to that drag coefficient. So this is, I'm just using the power rule, right? I'm going to take this negative 1/2 and pull it down out front. So you're going to get negative 1/2. This mess is just a constant, 2fd over rho a to the 1/2 times c to the negative 3/2. Okay? And so that means that a change in velocity is equal to, you just multiply both sides by dc. So you get negative 1/2 2fd over rho a to the 1/2 multiplied by dc, so you get dc, and then this c to the negative 3/2 can be written as over c to the positive 3/2, right? I guess you could leave it as negative. So that's it, and then you just plug in your numbers. It says to find it if, oh, we know what c is, right? So we know that c is 0.15, right? And then you know all of your other values, so you plug in your numbers, and you end up getting the answer of 220 times whatever your change in the coefficient is, okay? All right, there you go, just as the bell rings.